So today I'm going to talk about self-explainable models, and in particular this model that we recently proposed, which is a self-explainable prototypical variational model called ProtoVAE. To start with some of the background, explainable AI, as most of you already know, can be categorized mainly into two categories. So one are the post hoc explanations, which provides the decisions first, and then we can get some explanations with the help of some of the methods, which are post hoc methods. But the model here stays black box in itself. Then on the other hand, we have self-explainable models, which provides the decisions, for example, labels for a classification problem, and the explanations at the same time. And I personally like to call these models as glass box models because they're not as much as black box anymore, but yeah, still quite. So what is explainable AI? So this was very beautifully explained by Bean Kim in her ICLR 2022 keynote. It's a language of AI with which it can talk to humans. So if you see here on the left, if the red circle is what humans know, and on the right, that is what machines know. And then we have the intersection, which will tell us the output of our problem statement, for example, which label. Now, the explainable AI, and in particular, self-explainable AI comes in, where it tries to expand the knowledge of the machines and tries to get more overlap with what we know, what humans know. So in addition to which label, we also get why. Why is explainable AI important? So you already heard the example of Clever Hans in yesterday's tutorial. So I'll not mention that, but I have one more example. So it is about capturing unwanted bias in the data set. So this was a project, a very big project called Gender Shades, done not so long ago. So they scrutinized very famous facial recognition softwares from Microsoft, Face++, and IBM. And they tried to just classify male and female, but also they had the labels for the different skin shades. And what they found out was, very interestingly, that the models were biased towards darker skin shades and also females. So for example, 93.6% of the faces that were misgendered by Microsoft were those of the darker subjects. So if we have a black box model and we don't know what we are trying to find out, which bias we are looking for, maybe we'll never know what is happening. But later in this presentation, I'll show you how self-explainable models can be helpful in this scenario. So now, what are concept or prototypical based self-explainable models? So prototypical self-explainable models try to learn the representatives of a class. So they try to learn the most commonly occurring samples of a class. For example, this is for the quick draw dataset, and this is a dataset from Google where people just drew the cats and dogs, for example, in Pictionary, and then they created a dataset out of it. So these are the prototypes learned by our model, which I'll start explaining next. So these are 10 prototypes learned for class cat and class dog. And so what is very important here is, instead of looking at millions of images from class cat and class dog, you can just look at these 10 images and see what kind of cats people actually draw mostly. Yeah, and what kind of dogs people draw or prefer to draw. So now moving on, self-explainable models are very new in themselves. They have been around for just 3-4 years max. So the problem is there are no quantitative or qualitative measures in place yet for quantifying these models. So in this paper, we started with defining these three predicates, which can form an umbrella over all the existing self-explainable models, and we can actually categorize different models. So the first one and very important one is transparency. So a self-explainable model is transparent, according to us, is if the concepts or the prototypes are directly related to the downstream tasks. And secondly, the concepts should be visualizable in the input space. So they should be in human understandable form, like the ones I showed you in the previous slide. So they were in the form of human understandable images. Then the concepts should be representing non-overlapping information. So they should capture all the information basically present in the training set, and they should always be non-overlapping. Then we should have the trustworthiness. So generally the performance drops when we are using self-explainable model over the black box. That should not happen. Then the trustworthiness should also be in the terms of explanation. So the explanations should be more precise and more robust. These are some prior self-explainable models, very famous, ProtoVAE, and they have been used, many times, but they do not fulfill all three said properties. So in this work, we have proposed a new prototypical self-explainable model, which is probabilistic because it's based on variational autoencoder. And I'll show you in the next slides how it's transparent, diverse, and trustworthy. So it is diverse because of its architecture. So let's just dive into the architecture. So here, if you look at the top part, it is just a VAE, right? We have the encoder, we have the approximated posterior, we sample from it, and then we have the decoder. But in addition to that, we have some prototypes, which are basically, each prototype is a small Gaussian, and they lie in the same space as our latent vector Z, and they are of the same dimension also as a latent vector. And what we do is we find the similarity between our sampled vector and our means of the prototypes, and then we'll have a similarity score for each prototype, and we'll pass that through a classifier, which is just a linear layer. So this classifier, it's a linear layer, it's explainable. So the prototypes are directly connected to the last layer, to the classification task. So it's transparent. On the other hand, we have the decoder, which is also learned with the whole network. And we can directly visualize our prototypes in the input space with the help of this learned decoder. So concepts or the prototypes are in human understandable form through that. So we have the fully transparent architecture. And also, because we have I'll show you the losses in just a few minutes, but because of the presence of the variational autoencoder and all the regularization that we do with the help of the KL divergences, we have a very regularized and very transparent latent space. And I like to call this as a prototypical space, which kind of looks like this for MNIST. So this is the UMAP for a latent space. And these images that are shown that are overlaid over the UMAP are actually the prototypes. So the latent vector as well as the prototypes lie in the same space. And now, because everything's regularized, we can interpolate between the within class prototypes and also different class prototypes. So whole space is visualizable in input space. Then we have a transparent architecture, but what about diversity and trustworthiness? So we have three losses here for ProtoVAE. First is a very simple cross entropy, which ensures interclass diversity. Then we have orthogonal loss, which is basically which is trying to make the within class prototypes orthogonal to each other. So they'll try to represent more diverse information in the latent space, and that's why they are representing intraclass diversity. And then we have the VAE loss, which ensures robust classification and reconstruction. So we have the reconstruction loss, and then we have the scale divergence. So what is happening here is we are learning a mixture of VAEs. So we are trying to make our approximated posterior closer to prior, which is centered on the prototype. And all of these, for each class, all of these are weighted for its similarity with its similarity score, the similarity score of the sample to the prototypes. So if a sample is more closer to a particular prototype, its distribution will start moving closer to that prototype's prior. So these similarity scores act as our mixture weights, and then we have our different mixture of VAEs. Now, for the predictive performance and the trustworthiness of the model, so ProtoVAE for all these data sets tested here is performing better, and also we have compared with previously existing self-explainable models. And on the top of that, we also compared with black box encoders. So we just take our encoder, same encoder that we use in ProtoVAE, and we remove all the regularizations, everything. We just add a final fully connected layer. We train with cross entropy, and ProtoVAE is doing equivalent and even better in most of the cases to the black box model. So we are not losing on accuracy at all. Then the explanations are actually twofold. So we get global explanations and local explanations. So global explanations are the prototypes that are learned, and they represent what the model has learned, right? So for this model, we trained ProtoVAE with celeb-A dataset, and for male and female classification, we had 20 prototypes per class. And what is interesting to see here is, like I mentioned before, about biases in the data. So if we just look at the male prototypes, there are extremely few darker male prototypes present here. So we can directly get a sense of biases present in the data with the help of prototypes. And we don't have to look at millions of images for the class. Then we have local explanations. So why is an input classified as a particular class? For this, we use prototypical relevance propagation. It's basically built upon layer-wise relevance propagation, but the similarity score for a prototype is back propagated to an input. So what we get in the end is these pixel-wise heat maps. So we have our test image. What we get is that this test image is classified as class 5. But why? Because it is closer to this prototype, and this prototype, because of this area in the image, and with the 0.5 as the similarity score, for example. Finally, we also compare ProtoVAE's explanations with ProtoPNet's explanations, and below we have the ProtoPNet's explanations. And as you can see, the explanations are very coarse, and we would never know what is happening in the heat maps unless we overlay that on the original images that are on the most bottom row. And then also it's kind of fuzzy, but yeah, we are getting more fine-grained explanations. And that's it. And to conclude, we propose a transparent self-explainable model. It generates trustworthy explanations, and it performs on par with the current existing self-explainable models, as well as the black box encoders. The code is on the GitHub. The QR code is here. And also, if anyone has any questions, you can reach me on email anytime. Email is mentioned here. Thank you so much for listening to me.